Okay, so I'm continuing with chapter 17, but because I'm used to writing out what I'm about to write out on the board, we're going to do it that way. I've switched one slide from the transport and distribution in the body slide. 3 slides down, I've moved that slide up to be the one right after this title slide. Okay, just so you know. So let's talk about the hormones. So hormones go through the blood, and what that means is technically they get distributed through the body pretty quickly. They diffuse through the capillary wall, they enter the interstitial spaces, and the rate of movement varies by the type of hormone. So pretty much we're going to build on this outline that I'm about to do on the board, or this concept map that I'm going to do on the board, because technically, pretty much for the majority of the rest of the chapter, we're talking about the same thing. We're just kind of talking about it from different angles. So we have 2 types of hormones. We have lipid-soluble hormones, and we have water-soluble hormones, okay? So I'm gonna write that up here. So we've got lipid-soluble hormones, that's one type of hormone that we have. And then over here, we've got a terrible marker that doesn't write. Fantastic. Let's try this one. Water-soluble hormones. Pretty much everything that we're going to talk about from this point on is going to be dealing with these 2 categories, okay? So, lipid-soluble hormones. You have to remember that if we're talking about moving from one side of the cell membrane to the other side of the cell membrane, the rules from AMP1 still apply from chapter 3 in AMP1, when we talked about the fact that those lipid tails in the phospholipids don't just let things willy-nilly in and out unless they were lipid soluble. So if we've got lipid soluble hormones, then we have something that will go through that capillary wall with no problem. So they pass through the capillary wall easily, okay? They don't have any issue getting through. They can just go. Now, something about lipid-soluble hormones, though. If it's a lipid and I want to put it into the watery environment of the blood, is it going to like it? No, it's not. Lipids and water don't get along. Don't believe me? Put oil and water together, see if they mix. They don't. So, when we put lipids into the watery environment of the blood, we can't just go, you're free, because the minute they hit the water, they go, oh, I don't like that. So what do? Well, we put them in something called a transport protein. So if this is a lipid, again, and I try and put that into the blood, it doesn't like it. I've got this transport protein. Now remember, proteins are big, they're 3-dimensional. I can make them very, very complex. I can put the lipid inside of that protein and then have that protein close up and basically act like a transporter. That's why we call them transport proteins. Out here, it likes water. In here, it doesn't like water. So if I put this lipid in here where it already doesn't like water and fold it up, this traveling in the blood, no problem. And this lipid is literally hidden inside, so it's none the wiser that it's floating through the watery environment of the blood. So when we talk about the lipid-soluble hormones, they travel through the blood bound that big to a transport protein. They don't just float fancy free in the blood. They have to be bound to that transport protein. Now, when it comes to water-soluble hormones, they really have a hard time getting through membranes. Remember that with water-soluble hormones, the tails are not gonna like them in those cell membranes. So with water-soluble hormones, they have to go through, sorry, that's the wrong marker. In order to get to the blood, or get into the blood, they must pass through fenestrae, also known as windows, in the capillary. Okay, so if you've got a capillary and you've got this, you've got this water-soluble hormone in the tissue that needs to get in here, there have to be windows or spaces big enough for this to actually get in and then start moving through the body. It doesn't just magically happen. There have to be kind of accommodations made for that. Now, the capillaries of organs that are regulated by the glands, organs regulated by and glands secreting. Okay, got it. If I am a gland producing a water-soluble hormone, or if I'm a gland that is going to be influenced by that water-soluble hormone, I have to have the windows in my capillary. I have to have these big, huge spaces that allow this to move in and out of my capillary, okay? It's an accommodation that has to be made. Now, with water-soluble hormones, something else that's very, very different. I make them as I need them. So when we talk about a reaction for a water-soluble hormone, normally water-soluble hormones are kind of slow. So if you look at the last bullet under water-soluble hormones, they get into the tissue at a slow rate. So they're slow to get into tissue. Okay? It's not a quick process. Now let's go back to lipid-soluble hormones. Remember that with lipid-soluble hormones, they are traveling bound to the transport protein. And I'm taking something that was the size of this cap, and I'm putting it into a transport protein, making it this big. So I'm taking something this big, and I'm making it that big. That's a huge difference in size. And I do bring it up for a very specific reason, because that difference in size actually means that we kind of can create a storage system inside of our bloodstream, okay? So let's say that in the tissue, okay, I have to have 4 triangle hormones. Okay? Just making stuff up, but let's say that I do. At any given time, I need 4 of these working in order for my body to function optimally. Eventually, hormones wear out. It's just fact of life, they do. So push comes to shove, if I lose one of these, and then I have to send a signal to the gland that makes it, and then they have to start from scratch making this hormone, that's time that I don't have, okay? So one of the benefits of being a lipid-soluble hormone is that in the bloodstream, these lipid-soluble hormones are present, but they're bound to the transport protein. Remember I said they don't like the watery environment of the blood, so I have to bind them to a transport protein, right? Now, earlier I mentioned that if we have a combo, like a glycoprotein, that's a combination of a sugar and a protein, then enzymes kind of tend to leave it alone, because usually you have a protein enzyme and the protein enzyme goes, ooh, and then it sees a sugar and goes, oh, right? This combo of having a transport protein with a lipid inside kind of does the same thing. So these bound lipid-soluble proteins can float around in the blood for quite some time. Again, why is that important? Well, because in all honesty, that creates kind of a savings account for me. It creates a reservoir of this specific hormone in my bloodstream that is just waiting. So if I do, let's say, lose one of my 4 triangle hormones that keeps my body running well, I don't have to send a signal to a gland and have that gland start producing it and then wait for that gland to produce enough that it gets in the bloodstream. Literally, all I have to do is take this out of its transport. It's going to leave the bloodstream lickety split and go into the tissue. So when it comes to lipid-soluble hormones, the binding of them to that transport protein basically means that they don't rapidly diffuse out of the bloodstream. They stay there, and they just kind of continue to go the course. They keep going around and around and around. Why? There's no reason not to. Nothing's breaking them down. As well, as I said, it gives us a reservoir. It means that we've got this savings account of hormone in our blood so that when we do need it, it's automatically there. There's no wait time, okay? So you kind of got this constant replacement rate. Now, let's say for the sake of argument that 6 triangles bound are the normal number that you have in your bloodstream. Well, when I took this one out, now I have 5, right? Only have 5. That's when the signal goes to the gland, and the gland goes, okay, I need to make some more and put those in the bloodstream. And it replaces whatever was taken. The thing is, you'll notice that I very intentionally have 4 in the tissue and 6 in the bloodstream. So even if all of these go out at the same time, all 4, I've got enough in the blood to replace them, okay? So it isn't, it isn't just, one-time thing. This is constant. This is how it always works. Or not. Okay, so again, unbound, bound. This is what we've been talking about this entire time. Unbound hormones. This is what we call these. They're water soluble. Unbound. Why are they unbound? Because they don't mind being in water. I can just dump them in and they're good to go. No big deal. When it comes to lipid soluble though, if you look down here, lipid soluble have to be bound to a binding protein. They can't just float around. It doesn't work that way for them. Why? Try to put oil in water. Doesn't work out well. They don't like it. They don't like being there. Where's the mouse? Okay. Or not. Just had you. There. So, the bound lipid-soluble hormones, they're not permanently bound. We're not super gluing them to their transport protein. They're reversibly bound, meaning that once they're in the place they're supposed to be, it opens up and it lets it go. It doesn't stay bound to it forever, okay? There is an equilibrium established between the bound and unbound counterparts. Like I explained earlier, maybe it's 6 in the bloodstream for 4 in the tissues. That balance stays there. So again, if I lose one from here, I send a signal to the gland to say, hey, we need 6 again. You've got to replace that, okay? Bound are also trapped within the confines of the capillary. So remember I mentioned the size difference? That size difference also means that it can't just filter through. It would be like me saying I'm going to put a potato in a sieve that I make spaghetti in and the potato is going to go through the holes. It won't fit. Going from something that's the size of a cap of one of these expo markers to something that's the size of my fist automatically means that you're not going to just be filtering things out. We already went through it serving as a reservoir, and what that means is if one in the tissue is used, we've got one that's in the blood that can just be released automatically. Again, no wait time. These can also remain in the blood longer without being destroyed. That combo thing, again, kind of gives it that longer shelf life that I've been talking about. All right. So, metabolism and excretion. Destruction and elimination of hormones. There kind of has to be a time limit for how long these things work. We don't want them working all the time, especially if we're talking about something like adrenaline or epinephrine and norepi when we go into fight or flight. If we're going into fight or flight, we don't want that lasting long term. When it does, bad things happen. Okay, your body is not meant to be in that fast forward gear for huge long periods of time. So the body's activities can increase or decrease depending on how long a hormone remains in the body. One of the concepts that you need to understand is half-life. Half-life is, I'm going to read this, the length of time it takes for half the dose of a substance to be eliminated from the circulatory system. Its rate. How fast does it go away? Now you might be going, okay, so why don't we just say we've got this much and it goes this fast? Well, because we never know exactly how much is there to begin with. If we know how much is there to begin with, then yes, we can reasonably mathematically calculate how long it's going to last. But when we're talking about somebody's body and what somebody's physiology is doing, your physiology and your friend's physiology and his friend's physiology and me, all of them are different. So we don't have that, this is what we started with number. So what do? Well, instead of calculating how much, we know how quickly something disappears. So if we take a blood sample and we get that amount that's there at that time point, we know that it takes this long for this much to go away. So we can actually better calculate and figure how long that amount that we found when we did the blood work is going to be there. So The time to eliminate an entire amount isn't helpful, like I said, because it depends on what you start with. And again, my body versus your friend's body, your kid's body, your mom's body, all different. Knowing how fast something goes away, regardless of how much is there, helpful. Okay? So, times also vary depending on what the specific hormone is. Some hormones have really, really long half-lives. Others are a few seconds. So when I was working in labs, the way that we kind of used half-life, okay, the way that we did that, we used it as a method of determining how long something was radioactive for. And I used two specific radioactive isotopes. One was radioactive phosphorus. Radioactive phosphorus was basically half as radioactive in 3 weeks. So if I got a milliliter of radioactive phosphorus, I knew that in 3 weeks, only 500 microliters would be radioactive. In 6 weeks, it would be 250. In 9 weeks, it would be 125 microliters. So literally the amount of radioactivity, kind of petered out pretty quick. But I also used radioactive tritium at one point. Radioactive tritium has a half-life of 80 years. Huge difference in the amount of half-life. So if I were to use radioactive tritium and have a milliliter of that, yeah, that whole thing would pretty much be radioactive until I die. So knowing half-life, knowing how long it takes, is a bit more accurate in the way we calculate things. So let's talk about ways to lengthen half-life. How do we get something to last longer? How do we get something to basically stay active longer? Okay, 1, binding proteins. Remember I told you it gives it a longer shelf life? Gives it a longer shelf life. If you actually put it with something else like that, it makes it last longer. 2, structures. We just talked about the different types of hormones, and I talked about glycoproteins, right? And the fact that you've got a combination of a protein and a sugar. When you have combinations like that, it means, like I said, that the regular enzymes that would go after it are kind of confused by what they're seeing. Now, will it mean that it will never, ever? No. But it does mean that it lasts a little bit longer. There are four major ways to get rid of hormones from our bloodstream. 1 is excretion. Basically, dump it. So we make a hormone, it does its job, it gets filtered out in the kidney, and when we pee, there it went. Okay? We're not changing it, we're not breaking it down, we're not doing anything like that. We're literally just urinating, and there it goes. We dumped it in the garbage, and it gets dumped out. Okay? That's excretion. Metabolism is different. Metabolism actually means that we're going to break it. We're going to enzymatically break it down into parts and pieces. That would be like me going to your car and taking the wheels off and taking parts of the engine out. The car's not going to run anymore because I've enzymatically degraded it. I've taken it apart. Now, normally when you do that, eventually it does end up either in the urine, those parts and pieces end up in the urine, or they end up in the bile. But either way, the broken down pieces, they get excreted out of your body too eventually. But even if that didn't happen, because I broke the hormone, it wouldn't work anyway. Active transport. So, like most things, if you've got something that's really expensive, you're not going to use it once and then throw it away. Oh, how about a car? I used it once. Yeah, no, right? So Some of the hormones that we make are very expensive for us to make. They cost a lot of energy for us to make. So when we've got those types of hormones, we actually release them and then we bring them back. And then we reuse them. And then we bring them back. We don't just release them and let them go out in the urine because it costs too much to make them. So that technically is a way to remove the hormone from the blood, because it's not in the blood, it's back in the cell that made it. So that type of removal is called active transport. Literally, I'm letting it go and then I'm pulling it back. Okay? Conjugation. Okay, so to conjugate means to attach something to it. Okay, so I've got a hormone, it's active, I attach something to it, can't work anymore. Okay, so with conjugation, it's kind of a couple of things. One, if this is how it works and I put something here and those fingers can't move anymore, it's less active, it doesn't work as well. And it is a way of basically taking it out of the blood in the fact that it's not there to work anymore because it's basically been taken out of the equation. Some of the other ways that we can conjugate that kind of get rid of it, literally some of the ways that you change these, it actually makes it easier for things to find it and break it down. It makes it easier for your kidney to get rid of it. So when you alter it, you do one of two things. You're either going to alter it and it's going to be useless, or you're going to alter it and make it easier for you to do something else to it so that it's easier to get rid of. Okay.